Hello, Matt here from ChemistryStudent.com. In this video, we're going to look at the equilibrium constant, Kc. We're going to talk about what equilibrium constants are, how to calculate Kc and its units, and look at the link between Kc values and positions of equilibrium. Equilibrium, Le Chatelier's principle, and the equilibrium constant Kp have been covered in separate videos. Check the links in the description below. Before we talk in detail about equilibrium constants, there are a few essential ideas you need to be comfortable with. A reversible reaction is one in which the reaction can proceed in both directions. Reactants can react to form products in what is called the forward reaction, and these products can also react to reform the reactants in what is called the backwards or reverse reaction. In a closed system, reversible reactions reach dynamic equilibrium when the rates of the forward and reverse reactions are the same, meaning concentrations of all reactants and products are constant. Positions of equilibrium describe how the concentrations of products compare to the concentrations of reactants in an equilibrium mixture. If there is a higher concentration of products compared to reactants, the position of equilibrium is said to lie to the right. If there is a higher concentration of reactants compared to products, position of equilibrium is said to lie to the left. Recap done? Let's go. The position of equilibrium for a system can be considered as a ratio of the product to reactants in the equilibrium mixture. We can easily describe a position of equilibrium as lying to the left or right by looking to see whether there are more reactants compared to products or more products compared to reactants in the equilibrium mixture. If we want to know the exact position of equilibrium, however, we need to compare the actual amounts or concentrations of everything in the mixture. To do this, we divide the concentrations of products in the mixture by the concentrations of reactants. The value obtained is referred to as an equilibrium constant, represented with a capital K. There are several different types of equilibrium constant, but the most general one used is based on molar concentrations and is called Kc. The K stands for equilibrium constant, and the little c means it's based on molar concentrations of substances in the equilibrium mixture. Like all equilibrium constants, Kc is a ratio of products compared to reactants in the mixture, essentially a fraction. Products go on the top of the fraction and reactants on the bottom. We are basing the ratio on the molar concentrations of everything present at equilibrium, and we show concentration in chemistry using square brackets. Anytime you see square brackets in an expression, they are referring to the concentration of the thing inside the brackets. For example, square brackets H2 means concentration of H2 in moles per decimeter cubed. We also need to take the reacting ratios given in the reaction equation into account when calculating Kc. To do this, we raise the concentration of a substance by its molar ratio or coefficient in the equation. For example, hydrogen and iodine, H2 and I2, form an equilibrium system with hydrogen iodide, Hi, as the product of the forward reaction. To write the Kc expression for this system, we would put the product concentration, Hi, on the top of the fraction, square brackets remember, and the concentrations of the reactants, H2 and I2, on the bottom of the fraction multiplied by each other. The molar ratios or coefficients for the reaction of H2, I2 and Hi are 1 to 1 to 2. Meaning in the expression we raise the concentration of H2 to the power 1, I2 to the power 1, and Hi to the power 2. Anything raised to the power 1 just means the same value, meaning we can simplify this down to concentration of Hi squared divided by concentration of H2 times by concentration of I2. Really important to understand that the concentrations being used in the expression are the concentrations of everything at equilibrium. It's like taking a snapshot of the system whilst it's at equilibrium and using the concentrations of everything at this moment in the Kc expression. If the value calculated is 1, this means the product concentrations, top of the fraction, are balanced with the reactant concentrations, bottom of the fraction. They cancel each other out. The position of equilibrium is said to lie in the middle. If the value calculated is greater than 1, this means there is a higher concentration of products than reactants, as a larger value divided by a smaller value will always give a value greater than 1. The bigger the number, the more products there are compared to reactants, and the more the position of equilibrium lies to the right. If the value calculated is less than 1, this means there is a higher concentration of reactants than products, as a smaller value divided by a larger value will always give a value less than 1. The smaller the value under 1, the more reactants there are compared to products, and the more the position of equilibrium lies to the left. This can all be summarized in a general form called the equilibrium law, where for a general reversible reaction such as A plus B forming an equilibrium system with C and D, the Kc expression would be concentration of C to the power of its molar ratio times concentration of D to the power of its molar ratio, divided by concentration of A to the power of its molar ratio, times by concentration of B to the power of its molar ratio. Now, the value of Kc obtained for a particular reversible reaction at a specific temperature is constant. This means that the ratio of product concentrations to reactant concentrations will always be the same for that reaction at equilibrium at the same temperature. If the ratio of products to reactants in a mixture isn't the same as the Kc value for the reaction, the system hasn't reached equilibrium yet. This links into our understanding of equilibrium systems and Le Chatelier's principle. As the value of Kc has to be the same at a given temperature, if the concentration of something in an equilibrium mixture is changed, the concentrations of everything else will then also have to change to make sure the ratio of everything gets back to the value of Kc. For example, with the hydrogen and iodine system we just looked at, the value of Kc is always the same at a particular temperature. At 710 Kelvin, for example, the value of Kc is 0.02. This means the concentration of Hi squared divided by the concentrations of H2 and I2 times together must always equal 0.02 if the system is at equilibrium. If we were to increase the concentration of Hi in the system, this would mean the value on the top of the fraction would get bigger. If the concentrations of everything on the bottom of the fraction stayed the same, the value obtained would no longer be 0.02, as you would now be dividing a large number by the same value as before. The only way the value can be 0.02 is if the top of the fraction gets smaller and the bottom of the fraction gets slightly bigger, until eventually, when they are divided, the value equals 0.02 again. In other words, the concentration of Hi has to decrease a little bit and the concentrations of H2 and I2 increase. This is just showing us Le Chatelier's principle. When we increase the concentration of a product, the position of equilibrium moves to oppose this change, and this causes a decrease in product concentration and an increase in the concentration of the reactants. Just like when we increased concentration of Hi in our example, the equilibrium shifted to decrease it back down again and increase the concentrations of H2 and I2 until when divided by each other, the Kc value was the same as before the concentration of Hi was changed. I've mentioned a few times here that Kc is for a specific temperature. This is because the value of Kc changes with temperature. For a reversible reaction, the forward and reverse reactions are affected differently by changes in temperature. Meaning if the temperature of a system at equilibrium is changed, the rates of the forward and reverse reaction change differently, meaning they will no longer be the same and the system won't be at equilibrium anymore. Once a new equilibrium does get established, the concentrations of reactants and products will have changed and the ratio of products to reactants will now be different to the ratio at the previous temperature, meaning the value of Kc changes. Massive key point here, temperature is the only thing that changes Kc values for a given system. One area of potential confusion lies with the units of Kc. The units for Kc are based on the given reaction system and can be different for different reactions. As the expression for Kc uses molar concentrations, which have units of moles per decimeter cubed, Kc itself can have units which are based around moles per decimeter cubed. The easiest way to determine the units for a Kc expression is to substitute moles per decimeter cubed into the expression in the place of concentration values, and then cancel them out from the top and bottom of the fraction. For example, the Kc expression for H2 plus I2 to 2I is, as we've seen, concentration of Hi squared divided by the concentration of H2 times by concentration of I2. If we substitute in the units for each concentration, we end up with moles per decimeter cubed squared divided by moles per decimeter cubed times by moles per decimeter cubed. Moles per decimeter cubed squared is just the same as writing out moles per decimeter cubed times moles per decimeter cubed. Now let's cancel the same sets of units on the top and bottom part of the fraction. There are 2 moles per decimeter cubed on the top and bottom, meaning they all cancel each other out and no units are left. Kc for this system then has no units. This doesn't have to be the case, and units can look a bit overwhelming sometimes. More complicated examples have been outlined in a video on Kc calculations. Check the links in the description below. So, to summarise, the equilibrium constant Kc describes the ratio of product to reactants in an equilibrium mixture based on their molar concentrations. At a fixed temperature, the value of Kc for a system at equilibrium is constant. Kc expression is based on the concentration of products divided by the concentration of reactants, raised to the powers of their molar ratios in the reaction equation. Generally represented as Kc equals concentration of C to the power of its molar ratio times concentration of D to the power of its molar ratio divided by the concentration of A to the power of its molar ratio times concentration of B to the power of its molar ratio for a reversible reaction of A plus B to C plus D. Kc value of 1 means position of equilibrium lies in the middle. Kc value of over 1 means position of equilibrium lies to the right and the equilibrium mixture contains a higher concentration of products than reactants. Kc value of less than 1 means position of equilibrium lies to the left and the equilibrium mixture contains a higher concentration of reactants than products. Kc changes with temperature, meaning Kc values are only for a specific temperature for a particular reaction. Temperature is the only thing that changes the value of Kc for a given reaction. Units of Kc can be different for different reactions and can be found using the Kc expression by substituting in the units moles per decimeter cubed for concentration values. I hope you found this video useful. Please check out other relevant videos in the links given in the description below and visit chemistrystudent.com for free notes and revision materials.